So, section 7.2 is all about U substitution. It's just more practice with a little bit more intense U substitution and knowing what to substitute for what. So, I'm just going to pick a couple problems and just go over how you would choose a good U substitution. So let's say you had something like this, 1 plus cosine of x to the 4th power, and then out here you had sine of x dx, okay? And you wanted to integrate that, and you're going to use U substitution. Remember, you're always looking, what you're always looking for, first of all, if you have something in parentheses taken to an exponent, generally speaking, you're looking to see if the derivative of what's inside is sitting out there somewhere. If it is, then you're going to want to make whatever's in the parentheses equal to U. Now that's not always true, but it is true a lot of the time. If you have something under a radical or something in parentheses, that's usually a good thing to set equal to U. So that's what I'm going to do here. I'm going to make what's in the parentheses equal to U, and then you always do the derivative of U. Well, the derivative of 1 is 0. Derivative, now remember we're doing regular derivative here, not antiderivative. But the derivative of cosine is negative sine, and after you've taken the derivative, you put that little dx there. Okay, so now you're looking back at your problem, and you're going to make your substitutions. So instead of this 1 plus cosine x, I have U to the 4th. So that's done. Now I just need to know, okay, what's sine x dx? Well, I have sine x dx here, it's just I have that little negative. So I have to get rid of that negative. So I'm going to divide both sides by negative. So you really have negative du is equal to, my pen got funky, sine x dx. Okay? So instead of that sine x dx, you're going to put negative du. It's a negative 1 times du. So I'm going to bring that negative all the way out so I don't have to worry about it. And then I have du here. Now you do your antiderivative. Now it's a lot easier. It's a whole lot simpler than all the sine and cosine and stuff. The antiderivative of U to the 4th is U to the 5th over 5. And then you put that negative back in there. And that's it. Now the last thing you do is just resubstitute back for U. So that gives you 1 plus cosine of x. That's U, and it looks like I have it to the 5th. I got to remember my negative out front. Over 5. Alright, so that's that one. I'm going to go ahead and do another one on this same little video. That's maybe a little bit less obvious. So here's one. Let's say I want to integrate and I have e to the 2x sitting up here. Whoop. And then I have 1 plus e to the 4x sitting right there. So remember, e is its own derivative, but we do have issues here. You might be tempted on this one. You might say, oh, okay, well, I'm going to take that whole denominator and set it equal to U. So let's say you decided to do that. Okay, and maybe you did this. And then you said, all right, well, the derivative of U, derivative of 1 is 0. The derivative of e to the 4x is e to the 4x. And then you multiply by the derivative of the exponent, which is 4. The problem you're going to run into, if you do that, is when you look back at your expression and you want to put everything in terms of u's, in the denominator, you would have u. But e to the 2x, there is nothing in your definitions here that tell you what e to the 2x is. So there's nothing really up here that's going to help you. Okay, so that wasn't the best substitution to make, because again, if it doesn't make it easy to resubstitute back, then you need to look at other things. So one other thing you might want to look at is, you just learned some inverse trig patterns. So if it doesn't have regular trig substitution, you might look, regular U substitution, you might look and say, well, does this follow one of those trig patterns? And if you, let me erase what I started here because we're not going to do it like that. And if you look at this one, okay, I do have the number 1 here, I do have plus. This does happen to be a perfect square because I have an even exponent. So this looks like it's going to be following that tangent format. So let's just try it out. And when we did that, when we did the inverse trig, we took just the part after the 1, so it was 1 plus, and we called it u squared. So we're going to set e to the 4x equal to u squared. And then you take the square root, which really means divide the exponent in half. So that gives you e to the 2x. And the derivative of u, so e is its own derivative. So the derivative of e to the 2x is e to the 2x times the derivative of the exponent, which is 2. And then you have dx. Okay, so now we can account for everything up here. So that means I have 1 plus u squared now on the bottom. And I have, oh, you know what, in pink, really I should have had a dx here starting out, sorry. Anytime you're doing integration, you always have your little dx thing. So I have e to the 2x dx sitting right there. Well, here's my e to the 2x, here's my dx. I just need to get rid of that 2. So divide both sides by 2. So you have 1/2 du is equal to e to the 2x dx. So my e to the 2x dx happens to be 1/2 du. I'm going to put the 1/2 all the way out. Now I have du on top. And now, with just a little bit of work, you can see that this is the inverse tangent pattern. So you get 1/2 tangent -1 of u. And the last step is just put the x's back in. So it's 1/2 tan to the -1. Here's what u is equal to. So it's tan to the -1 of e to the 2x power plus c. All right. So sometimes regular u substitution, maybe just grabbing something and setting it equal to u, might not work if you can't substitute back. So if that happens, look for these inverse trig patterns. Look for something that looks like it's following the tangent sign or secant pattern.